All right, so webinar, we have the pleasure of having Anton Izosimov from Arizona, and he was going to tell us about groupoids in fluid dynamics. So shoot it out, please.
Thanks, Rui, and thanks, everyone else and all the organizers. It's a pleasure. And so I will talk about the role of groupoids in fluid dynamics. And I will mainly talk about a particular fluid dynamical problem related to the motion of vortex sheets. But actually, most things that I will say are quite general and apply to many different settings in fluid dynamics as well. And so, can you hear me well? Okay, just checking. Okay, so I will start with something much more classical. So, namely with a classical description of incompressible fluid dynamics due to Arnold. So that was put forward like in 60s, quite a long ago. And the setting here is that we have a M, which is a Riemannian manifold, and maybe a domain in the Euclidean space, may have a boundary, doesn't matter, just any Riemannian manifold with boundary works. And but for simplicity, let's assume that the boundary is actually empty. So no boundary. And so in that case, we can consider in all cases, we can consider incompressible fluid dynamics on M. So there is a fluid velocity field on M that I'll denote by V. And incompressible means that it's a divergence-free vector field. And then this fluid vector field that will evolve with time, and its evolution is governed by the classical Euler equation, which looks as follows. So if we take the time derivative of V plus the covariant derivative of V with respect to itself, so this is supposed to be equal to the gradient of a certain function so I put a negative sign because the function has a meaning of the negative pressure. So that's the equation for the evolution of V. This equation also involves this other function P, but actually that's like this speed can actually be eliminated from this equation if you take the divergence of both sides, then that allows you to express the pressure in terms of the velocity. So this actually is a flow, it's a differential equation or a partial differential equation, if you like, in terms of the fluid velocity field. And it's a quite complicated equation. In particular, there are still many open questions, analytic questions about this equation. In particular, when the dimension at least 3, it's not known whether the solutions to this equation extend to the whole time axis or they're only local in time. So it's a very complicated problem in general. And what Arnold did in 1960s, he showed that this equation can actually be reformulated as a certain geometric problem. So, namely, what Arnold said is that, first he said, let's change the point of view a little bit. Instead of thinking of the velocities, let's think of motions of fluid particles around the manifold. And the way we can do this, we can consider some initial position of particles. So let's call it the reference position. And then, as the fluid moves around, these particles, they get to some new positions. And then, assuming the flow is smooth, if we consider the map taking the old positions of particles to the new positions, if the fluid flow is smooth, that's a diffeomorphism of the manifold. And moreover, because we consider an incompressible flow, well, that's going to be a volume preserving diffeomorphism. So therefore, the motion of a fluid, it can actually be considered as a trajectory on this space that I called S diff M. So that's the volume preserving diffeomorphisms. And that's, well, that's a group, obviously, and it can be regarded as an infinite dimensional Lie group. And then, well, what Arnold proved is that, well, on this Lie group, one can consider a Riemannian metric. And this Riemannian metric, it's specified by two requirements. First of all, it's a right-invariant metric. So it's invariant under the right action of the group on itself. Because it's right-invariant, you just need to specify this metric at the tangent space, at the identity to the group. And this tangent space is, by the way, just exactly the space of divergence free vector fields that we already talked about. And at this, so at the identity, the metric is just given by, well, basically the kinetic energy of the fluid, or, well, the L2 inner product. So it's just the integral of the inner product of V with itself over the whole manifold times the Riemannian volume. So this is just the L2 metric. So we define this L2 metric at the identity, then we spread it over the whole group using right translations. And then, well, the main result of Arnold is that if we consider the geodesic flow of this metric, then, well, this is precisely the Euler equation. So the Euler equation is the geodesic flow on this group of volume preserving diffeomorphisms for the above metric, for the metric that's given by the L2 inner product at the identity, and that's right-invariant. And well, this is of course not very precise because, well, the Euler equation here, it's not an equation on the group, but it's rather an equation on the velocity field. So it's not written in terms of motion of particles. But this just means that, well, so this geodesic flow here, it has a symmetry because the metric is right-invariant, therefore the geodesic flow is also invariant with respect to this right action. And we need to mod out by the symmetry, and then what we obtain is the Euler equation. So in more geometric terms, so this geodesic flow can be thought of as, well, it's a Hamiltonian system on the cotangent bundle to that group, with the Hamiltonian given by, well, the metric essentially, or the inverse of the metric. And then, well, the Hamiltonian is invariant with respect to the right action, so we can perform reduction, reduce both the symplectic structure and the Hamiltonian. And, well, if one reduces the symplectic structure on the cotangent bundle to the Lie group, that gives the dual of the corresponding Lie algebra. And the corresponding Lie algebra is just the algebra of divergence-free vector fields. And the Lie bracket on this Lie algebra is just the usual Lie bracket of vector fields. So what one ends up with is the dual to the Lie algebra of vector fields, and the Hamiltonian function is, well, it's just the L2 inner product. So that's another way to formulate Arnold's result, is that, well, this equation here, it's a Hamiltonian equation on the dual to the Lie algebra of vector fields, and with the Hamiltonian given by the L2 inner product. So that was a main observation of Arnold's, and while this result, it actually has a lot of applications, and a lot of things can be proved about the fluid motion using this approach. And in addition to that, well, this also has several different extensions, so one can consider other fluid related settings, and it turns out that, well, those admit a similar description if one modifies the group somehow. So for example, one can describe the magnetic flows using this approach by well, extending the diffeomorphisms group in a certain way. Then one can also describe certain compressible settings and so on. So many of these fluid dynamical systems, they all admit the description that, well, one has a certain infinite dimensional Lie group, and, well, usually a right-invariant metric, not always right-invariant, but some kind of a metric on that group, and then the corresponding fluid dynamical problem can be reformulated as the geodesic flow on that. But then, well, so even though it certainly does extend to many settings, there are also settings where it doesn't apply. So, for example, well, perhaps the simplest case where Arnold's setting doesn't apply directly is if we consider, well, fluid flows in the setting of moving boundary. With moving boundary, and, well, the reason it doesn't apply is quite obvious here, is because if you have moving boundary and then you'll need to consider diffeomorphisms between different domains, and, well, that's clearly not a group anymore because such things in general cannot be composed. And, well, already in this setting, it's clear that a more relevant setting to for this is a groupoid setting instead of a group setting, because, well, one still has this diffeomorphisms, but not all of them can be composed, so it looks more like a groupoid rather than a group. So I'll write a groupoid here. Today I will talk about a problem that's somewhat related, even though it's well, it's not exactly the same, and probably more complicated than fluid flows with moving boundary. So namely, well, the general setting where this fits in is, well, flows with low regularity. And, well, when I talked about this, the Arnold's case, so I said it's a diffeomorphism. So we need to consider the group of diffeomorphisms. So what that actually means, so Arnold actually considered C infinity diffeomorphisms, so infinitely differentiable. Then there was this work by Eben and Marsden where they showed that, well, finitely many derivatives is actually sufficient. But, well, this finitely many needs to be sufficiently many. So the flow it needs to be differentiable sufficiently many times. If it's too bad, in particular, if it's discontinuous, then the group setting doesn't apply. And today I will actually talk about certain kind of discontinuous fluid flows, and I will show that, I will try to explain that in that setting, the groupoid setting is, well, actually much more relevant, and that the group approach just doesn't work. And more precisely, what we'll look at is the problem of vortex sheet motion. So let me first explain what vortex sheets are. So again, we consider a Riemannian manifold, maybe a domain in the Euclidean space. And now in this Riemannian manifold, we will consider fluid flows which have a discontinuity of a certain kind. So namely, let's assume that inside this M there is a hypersurface that we call gamma. And the fluid flow, it's nice and it's continuous, and moreover it's smooth away from this hypersurface. And for simplicity, one can actually assume that this gamma splits M into two parts, even though that's not really important. It is definitely true locally, globally it doesn't matter, but it is convenient to assume so. So on both sides of gamma, we have, so here we have some fluid velocity field, which we can call V plus. And here we have a fluid velocity field that we can call V minus. And both of these fields, they are nice and smooth. But along gamma, we have a discontinuity. So they do not agree when we approach gamma. So this means that we are considering a fluid flow which has a break along a hypersurface. And this kind of break is called a vortex sheet. And while this is clearly something that's observed a lot in examples, like you can think of one layer of fluid just not moving anywhere, and then there is another layer that's sliding over it. That would be an example of a vortex sheet.
And Anton, sorry, is the hypersurface gamma, does it move with time or is it fixed?
So the gamma will be moving with time, because if gamma is not moving with time, then this is just equivalent basically to two Euler equations, because you consider complement to gamma and then you have fluid motion in each of these parts. So gamma will be moving, yes. So this gamma, well, we'll see that, well, the fluid sort of dictates how it will be. So yeah, the space that we consider is the space of vector fields that have a break along some hypersurface. That hypersurface is not fixed. So, and of course, well, we still need to have incompressibility conditions here, because we're still talking about incompressible fluid flows. And the incompressibility conditions here, well, the way to write them down is, well, one should consider this V plus and V minus as one single vector field which has a discontinuity, and then write down the divergence-free condition for that vector field. But because it's discontinuous, it doesn't make sense literally, but one can write the weak form of that condition, which is just equivalent to divergence-free means orthogonal to gradient vector fields. So we can write down the condition that this vector field of ours is orthogonal to all gradient vector fields. And then it gives the following conditions. First of all, the divergence of both of this V plus and V minus should be 0. Well, clearly that we should have for incompressibility. But there is actually an additional condition that's related to incompressibility on this hypersurface. And this condition is that, well, we consider V plus on gamma and we consider V minus on gamma, well, they both make sense. We assume that they both extend smoothly to the hypersurface gamma. And then if we subtract one from another, that should be tangent to gamma. So in other words, well, the normal components of this vector fields, they agree on gamma. And again, just intuitively, it should be clear where this condition comes from. So if it's not the case, so say if you are moving here on one side and here on the other side, then, well, there will be sort of a domain with nothing in it formed, and well, this clearly violates the incompressibility constraint. So this is our incompressible vector fields, and well, again, one can consider solutions of Euler equation that belong to this class. And well, what it means is, again, well, the Euler equation doesn't make sense for vector fields like that because things are not differentiable along gamma, but there is, again, a weak form of the Euler equation, which is, well, which is a way to explain what it means for something not smooth or even discontinuous to satisfy this equation. And then one can consider, well, weak solutions of the Euler equation which belong to this class.
I have a question. Does the do the velocities determine the motion of gamma?
So the velocity does determine the motion of gamma, and that's, again, well, something that, well, so far here there is no dynamics, but if well, the fact that it should be a weak solution of the Euler equation implies that gamma is actually transported by the velocity field.
By which velocity? The sum of the velocity?
It doesn't matter because we view gamma as an unparameterized surface, so only the normal component matters. So by any of them, because the normal component.
That's because the difference is tangent to gamma.
The difference is tangent. So the difference, what it only does, it kind of moves gamma along itself. So that doesn't matter.
Okay, and this implies that the volumes on the total volumes on each side of gamma stay.
The total volumes stay the same. Yeah. So this also follows from here. The total volumes on each side of gamma, they stay the same. Right? So the question we'll discuss here is how to describe this weak solutions geometrically and whether they can be thought of as geodesics on an object of a certain kind. And while the first result in this direction actually belongs to Christian Loschke. So it was, so I think the spelling is wrong. So it's like this. So a few years ago, it was in the result of his thesis that he wrote under Felix Otto. And what Loschke considers is the situation is like this, but it's slightly, less general. Namely, he in addition, he assumes that the vorticity of this vector field here, it's completely concentrated on gamma. And in other words, what this means is that if we compute the vorticities of this two vector fields, then it's just zero. And under certain topological conditions, that clearly just means that V plus, and so the situation he considers is that V plus minus are both gradient because they have zero curl, and if things are simply connected, that's gradient vector fields. And of course, because we want it to be gradient and divergent free, this U plus minus, they should be harmonic functions. So the situation considered by Loschke is that you have two harmonic functions in two domains. The flow is given by their gradients, and there is this additional condition that the normal components of the gradients, they do agree. And then what Loschke proved is that this motion actually can be thought of as geodesic motion. Namely, one needs to consider the following space. So here we have this gamma, which is our hypersurface, the vortex sheet, and the class of fields we are considering now, they are given by these harmonic functions, U plus and U minus, in the complement to this domain. But actually, as we know, a harmonic function is uniquely recovered from the normal component of its gradient on the bound. That's just a Neumann problem for the Laplace operator. So here, we do not really need to specify this U plus and U minus, but what we do need to specify is, we need to specify a section of the normal bundle to gamma, and that's the phase space. So the phase space here, it consists of pairs. So it's a hypersurface and also, a section of the normal bundle to that hypersurface. And this section is not arbitrary because we have the incompressibility condition in terms of this section. It constrains, it becomes a kind of a zero mean condition. So this section, because we have a volume form on a manifold, the section can be integrated over gamma, and that should result in zero. So that's the phase space. And actually one can observe here that, what is this phase space? So this phase space is, the section of a normal bundle to gamma, as we just discussed. This can be thought of as a tangent vector to the space of hypersurfaces, because well, if we have a hypersurface and we want to deform it, then an infinitesimal deformation is precisely a section of the normal one. Because, well, in general, you deform a surface with a vector field, but a tangent component will only deform it along itself. So what is important is a normal component. So this thing here is precisely the tangent bundle to the space of hypersurfaces. And well, again, not well, one also needs to say that it's, well, the zero mean condition here doesn't arise if it's space of all hypersurfaces, but what we need to do is fix volumes on both sides. So we say that the volumes are fixed, and in that case, and only consider hypersurfaces that confine fixed volumes on both sides. And in that case, the tangent bundle is precisely the space that we have. And then the result that Ljoške proved is that, well, we can consider two different things on this tangent bundle. One is the Euler equation. So we can take the weak form of the Euler equation, restrict it to this particular type, well, of solutions, and that gives a certain flow on this tangent bundle. On the other hand, well, because it's a tangent bundle, and if one has a metric on the space of hypersurfaces, then, well, any metric gives the geodesic flow, which is also a flow on the tangent bundle. And then, well, what Ljoške proves is that there is a metric on the space of hypersurfaces such that the Euler equation is precisely the geodesic flow of that metric. So the Euler equation is the geodesic flow of that metric. And one should say here that this Ljoške's metric, it's sort of complicated. So it's more complicated than the one that we saw in Arnold's description. So namely, well, one needs to define a metric on this sections of the normal bundle. The way it's done is that you consider all possible divergence-free vector fields on the whole manifold, such that if you restrict this vector field, you get a given section. And you consider the norm of the vector field, and then you minimize over all possible vector fields. So that's the metric. In particular, it's sort of non-local in nature. It's not, you cannot compute the metric if you only know a small neighborhood of gamma, but you need to know the whole manifold and the metric on the whole manifold. So the question is if gamma is assumed to be connected. So I will assume it in this talk, but it's not that important. Well, here, well, if the topology is more complicated, so really here, let's think of, like, for example, an n-dimensional sphere, and gamma is a sphere of the dimension 1 less, so that everything has sort of a trivial topology. If the topology is more complicated, then, well, certain modifications need to be done, but it's very similar. But for the purpose of this talk, let's consider the most simple situation. Okay, so so Ljoške proved that, well, the motion, well, this vortex sheet type solutions with gradient fields on both sides of the vortex sheet, they are given by, well, geodesics on the space of hypersurfaces. And, well, the question that I will, well, so first of all, let me say that what I'm gonna describe now is based on my joint work with Boris Khesin. And, well, this work of Ljoške was sort of one of the motivations for the work we did. And the question that we try to understand is that, well, there are kind of two different descriptions here. So there is this Arnold's description of smooth flows on one side. And in that case, one has geodesics on the group of volume preserving diffeomorphisms. So geodesics on here. And there is this Ljoške's description on the other side. And here, well, one also has geodesics, but on a completely different space and in a different setting, because here it's the flows are not smooth. So here one has geodesics on the space of hypersurfaces. And so the question that we were trying to answer is, well, what's the connection between these two? So how to get from a group to the space of hypersurfaces? How are the corresponding Riemannian metrics related to each other? And in order to answer this question, well, the thing that's natural to do is, well, Lyoshki considered only this gradient vector fields, and this is completely non-intersecting with Arnold's case, because in Arnold's case it's a smooth divergence-free vector field. It cannot be gradient globally, because then, well, we would have a global harmonic function, and in the compact case that's clearly impossible. So therefore, we consider the case which kind of extends both, and by considering this case that extends both, well, we'll see how these two things are actually related to each other and where the space of hypersurfaces comes from. So now we'll just again, well, return to this general situation where we have a vortex sheet gamma, and on two sides of gamma, we have our divergence-free vector fields satisfying our conditions. So the divergence is at 0. And also the difference on gamma is tangent to gamma. And now we want to consider weak solutions of the Euler equation in this more general sense. And well, this clearly generalizes both pictures. Well, not geometrically yet, but the equation that one gets here, it includes both a smooth case, which corresponds to the situation when gamma is just trivial, or maybe gamma is not trivial, but there is no actual discontinuity. And also it includes as a particular case this situation considered by Lyoshki when the vector fields on both sides are gradient. And well, this case, so the description we obtained in this case, it requires the introduction of a groupoid. And well, it's actually quite clear why the group setting will not work in this case. Well, of course, here things are still, well, one can still consider the fluid flow as Arnold did, because what Arnold said, well, instead of considering vector fields, let's consider the flow, let's consider how particles move. And then, well, here, if we consider the flow, then because we have a discontinuity in the velocity field, we'll clearly also have a discontinuity, well, in the corresponding map that describes the flow. So namely, the map, it will be a map of the following kind. So there is a hypersurface in the pre-image, and there is also a hypersurface in the image. And then, well, the map is a nice, smooth, volume-preserving diffeomorphism from one side to another, and from this side, from here to here. But well, there is actually no condition at all along this hypersurface. So along the hypersurface, it completely breaks down. It's discontinuous. So for the fluid velocity field, we actually had some kind of a continuity condition in terms on the hypersurface, but for the corresponding diffeomorphism, it just goes away. So now we have two completely unrelated diffeomorphisms on two sides of the hypersurface. And well, of course, one can still consider this as a global, well, self-map of the manifold, but then it's clear that maps of this kind, they do not form a group. If you compose two maps of this type, then what you get is just a complete nonsense. So you try to compose this with another map of this kind, but if this other map is discontinuous along some other hypersurface and they intersect in some weird way, then, well, it's just not going to be a map of the same class. And well, that's one indication that the group setting clearly doesn't work here. And another indication comes from, well, it's if we look at the infinitesimal level, so recall that infinitesimally, well, we need to consider vector fields which satisfy this divergence-free conditions and the condition of continuity of the normal component on gamma. And then, well, if this was, well, if the corresponding, well, fluid flows, if the corresponding fluid flows form the group, then, well, this thing here, it should form a Lie algebra. But then, well, a straightforward computation shows that vector fields of this kind, you consider the Lie bracket, then, well, it's no longer a vector field of this type. So this condition, it's not closed under the Lie bracket of vector fields. Well, of course, the first condition actually is preserved under the Lie bracket because, well, the bracket of divergence-free vector fields is divergence-free, but the second condition is not preserved. So if you have two vector fields that have this continuous normal component on gamma, you compute their Lie bracket, then the Lie bracket doesn't have to have a continuous normal component on gamma. That's just completely not true. The normal components on gamma that you get are completely arbitrary, so this is not preserved at all, which means that this here is not a Lie algebra. This is another indication that, well, we actually need to use the groupoid setting here, because as we know, in the groupoid setting, the corresponding infinitesimal object, it doesn't have a Lie algebra structure, but instead it's supposed to have a Lie algebraic structure. And as we'll see, that's indeed the case. So there is no bracket on vector fields here. So as we just discussed, well, these conditions here are not closed under the Lie bracket, but that simply means that in an algebroid, if you have two elements in the same fiber, you don't have the bracket. That's not well defined, but what's well defined is the bracket on sections of the algebra. So that precisely corresponds to the fact that we cannot take bracket of vector fields of this type. So, and then, so what we showed in our paper with Boris is that indeed the groupoid approach works nicely in this setting, that the Arnold's picture, well, completely generalizes if, well, one considers this kind of maps that arise here as a groupoid instead of a group. And well, the fact that it's a groupoid should be pretty clear from this picture here. So as we discussed, well, in general, we cannot compose maps of this type. So we consider this, so what we call discontinuous diffeomorphisms. And in general, such diffeomorphisms, they cannot be composed. But on the other hand, it's clear that if we have another diffeomorphism that has a discontinuity across this hypersurface, then, well, then things can be composed. So there is a partial composition here. And, well, namely, well, one can compose two discontinuous diffeomorphisms if the hypersurface of discontinuity in the image of one map coincides with the hypersurface of discontinuity in the pre-image of another map, and that's precisely a groupoid type structure. So we call this groupoid D as diff. So this kind of S diff was volume preserving diffeomorphisms, and this is discontinuous volume preserving diffeomorphisms. And well, what we show in our paper is that, well, this indeed can be regarded as a groupoid. So this, well, one can actually give a rigorous meaning to the, well, it's clear that it's a groupoid, but we show that it's also a Lie groupoid in the category of Frichet manifolds. So this actually makes sense to say that it's a Lie groupoid. And well, then we show that one can consider one can describe fluid dynamics in this setting in a very similar way to what Arnold did. So namely, well, one should consider, well, basically, so in the group setting, we had a group, and on a group, we had a metric, and this metric was right-invariant, and we need to look at the geodesic flow of that metric. Here, one needs to do something similar, but, well, the problem here, and this metric, it's actually, so the way you construct it, you have a metric on the Lie algebra, and then you use right translations to define a metric on the whole group. In the groupoid setting, it doesn't quite work. So if you have a metric on the algebroid, and then you use right translations on the groupoid, you do not get a metric on the whole groupoid. You actually get a metric on what's called the source fibers of the groupoid. So you have the source map on the groupoid, and well, you fix the value of the source map, that gives you the source fiber. So have a question from Alan in the chat. So yeah, okay, yeah, that's a good. So let me describe accurately what this groupoid is. So okay, so this groupoid, it's a groupoid over, so the base of this groupoid is the space of hypersurfaces. So it's a groupoid over the space of hypersurfaces. And again, these are just not arbitrary hypersurfaces, but it's better to restrict to those that confine fixed volumes on both sides. So we have hypersurfaces confining fixed volume. It doesn't matter that much. You could consider all hypersurfaces too, but that would make the groupoid non-transitive. And so then, well, each element here, each arrow in the groupoid is a map of this kind. So we have one hypersurface, we have another one, and then we have actually two smooth diffeomorphisms on both sides of this hypersurfaces. And the source map and the target map here, so the source map is just the map that, well, associates gamma 1 with a given pair of maps, and the target map associates gamma 2 with a given pair of maps. So the space of objects of this groupoid is indeed the space of hypersurfaces, and then the space of arrows is kind of a pair of volume preserving diffeomorphisms that are sitting on both sides of the hypersurface. So that's the groupoid. And then, well, the result that we prove, it can be formulated as well as a geodesic description, but as I said, well, the geodesic description here is slightly more tricky than in the group setting, but it is somewhat easier to state the result in terms of the corresponding algebroid, because recall that in the smooth case, what we had is that the fluid motions were just, well, basically they were given by the Hamiltonian flow on the dual of the Lie algebra, and the corresponding Hamiltonian function is just the L2 energy. So it's Hamiltonian flow of L2 energy on the dual of the Lie algebra. So the result we prove in the setting of vortex sheet motion is that, well, one has a somewhat similar description here, but now, well, instead of the Lie algebra, we obtain an object that's called the Lie algebroid. And I will describe later on in more detail what this Lie algebroid looks like here. So for now, let me just say that it's an infinitesimal object that's associated to a Lie groupoid, to this Lie groupoid, and, well, have the standard result that if we have a Lie algebra, then the dual space of that Lie algebra has, well, it has a canonical Poisson structure. Therefore, we were able to consider the Hamiltonian flow of the L2 energy. So same happens for the dual of the Lie algebroid. But the Lie algebroid, it's not a vector space, but instead it's a vector bundle. One considers the dual bundle, and while that dual bundle is canonically a Poisson manifold. And then what we prove So this result concerns weak solutions of the Euler equation, which are of vortex sheet type. So these are solutions that have this discontinuity across a hypersurface. So we prove the weak solutions of the Euler equation of vortex sheet type. So they, again, while they can be described as the Hamiltonian flow, is the Hamiltonian flow of L2 energy. But here, well, instead of the dual of the Lie algebra, one needs to consider the dual of the Lie algebroid. And that's the Lie algebroid corresponding to this groupoid of discontinuous diffeomorphisms. So is a Hamiltonian flow of L2 energy on the dual of Lie algebroid of the groupoid of discontinuous diffeomorphisms. And while as I said, this result can also be reformulated in more Riemannian terms instead of Hamiltonian terms. And well, then one gets a description on a groupoid instead of an algebroid. But it's not a geodesic flow on a groupoid, but it's rather a geodesic flow on the source fiber of that groupoid. So in terms of this picture here, one needs to fix gamma 1 and then allow gamma 2 to flow. And well, that's the source fiber of this groupoid. And then, well, the result is that the weak, well, if we consider motion of particles due to the weak form of the Euler equation, well, then this describes geodesics on this source fiber of the groupoid. So this is the main result. And so far, I didn't say how this is related to Loschke's description. And well, in order to be able to answer that question, I'll need to explain in more detail what the algebroid here looks like. So I will now describe the algebroid. And then, well, as soon as we know what the algebroid looks like, we'll be able to see, well, that actually this description of Loschke is a particular case of this theorem. So namely, well, this theorem is saying that, well, we have a Hamiltonian flow on a certain Poisson manifold. And then it turns out that Loschke's description just corresponds to a particular symplectic leaf in that Poisson manifold. Namely, in some sense, one needs to take the most degenerate symplectic leaf, which doesn't quite make sense here because all symplectic leaves are infinite dimensional. But in some sense, one needs to take the smallest symplectic leaf. And that precisely recovers this theorem of Loschke about the geodesic flow on hypersurfaces that we discussed earlier. So now, well, let's discuss what the algebroid here is. So first of all, what is an algebroid in general? So recall that an algebroid is a vector bundle over a manifold B. So B is a manifold and A is a vector bundle over that manifold. And this vector bundle, it has an additional structure. And this additional structure is a bracket on sections. So think about the tangent bundle of a manifold. If you have a manifold, then the sections of a tangent bundle are vector fields. So there is a bracket on sections, a bracket on sections. And also, well, this bracket on sections, it is supposed to satisfy kind of a form of a Leibniz rule, similar, well, to what one has for the usual Lie bracket. The usual Lie bracket is sort of a differentiation in each argument in some, well, not quite, but there is some condition like that. And here, well, in order to be able to write down the Leibniz rule, well, if one tries to do that, one runs into a problem that, well, it does make sense if this is the tangent bundle, but in general it doesn't. So one needs to introduce one additional structure here. So this is the so-called anchor map. And the anchor map is a bundle morphism from A to the tangent bundle of B. So this is what the algebroid structure is. So it's a bundle morphism from A to the tangent bundle of B, and a bracket on sections of A. And these two structures are supposed to be compatible with each other in a certain way. And well, the simplest example, as I said, well, in the vector bundle is just the tangent bundle. The anchor map is the identity map, and the bracket on sections is the usual Lie bracket on vector fields. And the other extreme example, when B is just a point, in that case, well, this map is clearly the trivial map because the tangent bundle is trivial. And then the bracket on sections just becomes a bracket, and it's by bracket I mean a Lie bracket. It becomes just a Lie bracket on A, and A is a vector space. So in that case, it's a Lie algebra. So a Lie algebroid is something that generalizes tangent bundles on one side and Lie algebras on the other side. And there is a way to associate an object like this with a groupoid in a similar way to how associates a Lie algebra to a Lie group. And because there's discontinuous diffeomorphisms, they form, well, a Lie groupoid. The corresponding infinitesimal object should be a Lie algebra. And we've already described, so as a space, we already described this infinitesimal object. So our algebroid consists of these vector fields, well, that are smooth and divergence free on both sides of gamma and have the continuity of the normal component condition. And this, so this clearly has a bundle structure over the space of hypersurfaces. So what I draw here, it's simply a fiber over gamma. So because for each such vector field, there is a hypersurface is discontinuous across, well, that's the bundle projection. So this fiber is over the space of hypersurfaces. And well, one can show that it actually is indeed a vector bundle in the category of Frichet vector bundles. And then one should have these additional structures. So one part of the additional structure is the anchor map. And well, the anchor map should take an element of this vector bundle, so a vector field like this, to a tangent vector to the base. But the base is the space of hypersurfaces, so a tangent vector to the base is just a section of the normal bundle. And because we have this continuity condition, we can take V plus or V minus, restrict to gamma, and that gives the same section of the normal bundle. We simply project either V plus or V minus, we project it to the normal bundle. So project it to normal bundle. So that's the anchor map for this algebroid. And well, and additionally, one should have a bracket on sections. And recall that, well, when we try this naive way of constructing a bracket here, namely just taking the Lie bracket of vector fields like this, well, then we saw that this doesn't work, that our space is not closed under the Lie bracket. And well, it turns out that the actual formula for the bracket on sections, it still involves the Lie bracket of vector fields, but it does contain additional terms. So it's a certain modification of a Lie bracket on vector fields. So it is of the following form. So let's assume we have, well, one section and another section, and we want to compute the bracket of these sections. And well, this is again a section, so we can compute that we can restrict that section to a particular fiber. So we can take a particular hypersurface gamma and then look at the value of this, well, on the corresponding fiber. And it turns out that, well, the way it looks like, so the first term is you simply take V of gamma, which is a vector field discontinuous across gamma, take W of gamma, and then you take their Lie bracket. But the problem is that, well, this thing, as we discussed, the result of this, it's not within our class. Namely, it's something that divergence free on both sides, but the continuity of the normal component condition is not preserved. So, and because of that, there are certain correction terms here. And these correction terms, they actually recover the continuity of the normal component. And well, the first term, it's in some sense, it's fiber-wise. To compute the first term, you only need to know the values of your sections at a particular point. And well, that's normally a bracket in an algebra, it doesn't look in this way. And these correction terms, they are not of this type. So to compute the correction terms, you actually need not just the values of, well, this vector fields at a particular gamma, but you need to know them in the neighborhood of gamma. So there are certain additional terms here, which you need to add to the algebraic bracket in order, well, for the continuity of the normal component condition to be preserved. And well, the way one derives this bracket is, well, basically comes from the groupoid structure, because the algebraic structure is defined for the groupoid. So one can use the description of the composition in the groupoid to derive the expression for the algebraic bracket. It turns out that it's of this form. And well, so that's what the so Dima is asking if we can write down the correction terms. No, they are not too complicated. So the correction terms look like this. Well, first of all, in order to write them down, the algebra needs to be extended a little bit. Namely, let's forget about this condition. So if we forget about that, this gives us a vector bundle. It's no longer an algebra, but it's a vector bundle. So now this bundle just consists of, well, pair of vector fields that are divergence free and no condition on the normal component. And then, well, just by the nature of that vector bundle, in that vector bundle, there is a natural flat connection. So the way this connection works is, so assume you have a global divergence free vector field on your manifold. Then if you have such a global divergence free vector field, then whatever gamma you take, you can think of your vector field as a vector field that's discontinuous across gamma. And because of that, well, this thing gives you a section of the vector bundle. And there is a unique connection such that, well, unique flat connection such that, well, it's a flat section of that vector bundle. So if we extend the vector bundle a little bit, there is a flat connection there, and then the correction terms are like this. So we take W, and we regard this W as a section of that extended bundle, and then we take the covariant derivative with respect to our flat connection, and the direction in which we take it is the anchor map applied to V. And then there is, well, the opposite term, which is the derivative of V with respect to the anchor map of W. So these are the correction terms. And one can actually explicitly show that these terms indeed correct things in the way that the continuity of the normal component condition is recovered after one does this. So I think I have like 1 minute left. Thanks for the question, Dima. Well, one last thing I wanted to mention is connection to Loschke's theorem. So basically, as I said, the Loschke's result is recovered as dynamics on a particular symplectic leaf. So namely, recall that we have this anchor map. This anchor map is a bundle morphism that goes from our algebroid to the tangent bundle to the base, which is the space of hypersurfaces. And well, in general, for Lie algebroids, this is not just a bundle morphism, but this is it's a morphism of algebroids. It preserves the Lie bracket. And because of that, one can look at the dual map. And the dual map is the map between the corresponding dual bundles. And because we had an algebroid morphism, the dual map is a Poisson map. And if we assume that this initial bundle morphism is injective, not injective, but surjective, which it is in this case, then the dual is injective, from which it, well, pretty much follows that T star to the base embeds in the dual of the algebroid as a symplectic leaf. And then, well, what one needs to do, one needs to take our Hamiltonian flow on the dual of the algebroid, restrict it or pull it back to the cotangent bundle of the base of the space of hypersurfaces. And well, if one computes what the metric here, by the way, it's quite nice. It's just the L2 energy. But because of the nature of this map, the metric becomes non-local and complicated. And that is precisely this Loschke's description when you need to minimize overall possible divergence-free vector fields. So this just comes down to what this dual of the anchor map is. So in that way, Loschke's result, Loschke's geodesic description, it just follows from ours by restricting to this most degenerate symplectic leaf, which is the cotangent bundle to the base. And I think I will stop here.
Well, thank you very much. So we open the floor for questions. Please just unmute yourself. Oh yeah, we should, of course. Thank you. Sorry.
Thank you.
All right, so let's open the floor for questions then. And so anyone who has a question, please unmute yourself and just go ahead and ask your question.
I think Alan had a question.
Yeah, I was wondering, it looks a little bit like, there are two parts to it. It looks a little bit like what you're looking at is a free boundary problem on each side of the hypersurface, where these are linked by the fact that the hypersurfaces move the same way. And I'm wondering also that the first time I saw groupoids in this context was the thesis of Henry Jacobs, who was a student of Marsden. I'm wondering how your work might be related to what he did.
So regarding the free boundary case, I think it works better in the opposite direction. So the free boundary case can be thought of as a certain degeneration of this problem. But this problem, it's not exactly two free boundary problems, because there is also an interaction, basically because we have the condition that the normal components must agree, then these two sides are not independent from each other.
Mm-hmm.
So yeah, so I regarding the work of Henry, so I think what Henry was mainly concerned with the motion of the solids in or well deformable objects in fluids, and that's indeed another situation where the groupoid description applies. I think there's no direct relation between our description and his, except that both problems can be described by groupoids. But I would assume that so from what I remember, he says that it's a groupoid, but he doesn't compute all the structures. I would assume that, for instance, if one computes the algebroid in this example, it should be a pretty similar structure. In particular, this formula I wrote here, I think it's pretty robust. So somehow in all this type of problems, and this looks a little bit like action algebroid, even though it's not, but the formula very much reminds of the action algebroid structure. So I think this kind of an algebroid bracket shows up in a variety of related problems. So I would think that this is something that should be showing up in this setting discussed by Henry as well.
Mm-hmm.
Oh,
Thanks.
does that answer your question?
Yeah, it does.
Okay.
I got another question, if I may.
Sure.
Go ahead.
Hi, Anton. Thanks for a nice talk. So I have the following question. What if the domain is two-dimensional? Would it simplify some stories, right? There usually two-dimensional stuff, right? We have whatever, we have more tools in that. So then this boundary is just a curve. Do you have some more structure, some simplifications, or some thoughts on how it can be more manageable in the two-dimensional case?
So I don't think that in our setting things do simplify in the two-dimensional setting. I mean, well, in analysis side of the picture, things, well, then they're still very complicated even in the two-dimensional setting where you have vortex sheets, but there are much more analytic results in that case, because indeed well, the vortex sheet is a curve, so one can kind of parameterize it as a graph of a function, and then
perhaps let me be more precise. Is there some setup? Maybe you should assume something about the motion of your fluid where conformal transformations would be useful?
Well, that's a very good question. So I didn't think of conformal transformations in this setting, and I don't, but well, conformal transformations are definitely used to study the free boundary problem, which is a related problem. And well, well, again, it's not that they kind of simplify things drastically, but well, they do give some insights on how to tackle this. And I haven't thought of conformal transformations in the setting of vortex sheets. So while we do, the dimension doesn't matter much. It's,
okay.
Starting from 2, it kind of all looks similar.
Okay, thank you.
I think Dima has a question.
Yeah, Dima.
Hi. Let's see, am I visible now?
Yeah.
Yes, sure.
Or audible? Yes, yes, I just wanted to follow up on some of the previous questions. Because if I understood you correctly, so your setting involves a connected smooth hypersurface, splitting your manifold into 2 domains of fixed volume. Well, unfortunately, my knowledge of the subject is extremely limited, but in practice, can there be many of these vortex sheets with which can maybe mutate or degenerate in various ways as time evolves? And so have you considered, do you think your method would extend to this kind of like this more general situation?
Well, that's a very good question. So we can certainly allow for disconnected vortex sheets, which is the same as several of them. But our particular description applies as long as they do not hit each other, and in reality, they do.
Yeah, that's exactly what I was thinking of.
Yeah, I mean, this in general, like the vortex sheet problem, it's not very well behaved from the analytic point of view, so it exhibits blow up, so things stop being smooth in a finite time. So this our description is valid until things start go really in a really bad direction. So we didn't look at the situation when they start hitting each other, and I would say it's not really clear so far how to attack this. But it's a very good question, because, well, of course, people in analysis want to consider things like this because these things actually happen.
Can they also, for instance, can they degenerate developing self-intersections?
Yes, and again, well, that's what does happen in well, if you do like numerical simulations here, then yes, there are lots of things like that you will see. But we do assume that, well, gamma stays smooth and embedded, and well, well, the result is that, well, if we have a weak solution that stays in this class up to a certain time, then, well, this corresponds to this Hamiltonian flow. But, well, if it leaves this class, this means that our Hamiltonian flow blows up, and then it may evolve further, but in some other class of solution.
All right, thank you very much, and thank you for a very interesting talk.
Thank you.
I think Alan is raising his hand physically.
Yeah, I have another question. Thanks for your talk, by the way. It was really nice. Is there some relation between this and, or is there some groupoid approach to the problem of vortex filaments? I see that Boris has a paper on those also.
So that's a very good question. So for groupoid filaments is, well, we don't know how to describe that situation so far from like either group or groupoid setting, basically. And one of the problems that arises in the vortex filaments, well, simplest case of a vortex filament is just one single vortex in the plane. And the problem with the vortex is that when you approach a vortex in the plane, then the velocity field, it basically becomes infinite at this point. And in particular, well, the energy of this field is not well defined, as opposed to the vortex sheet case where the energy is defined because your fluid flow, it's discontinuous, but it stays, the velocity field stays bounded. So here it's unbounded. So while people doing analysis, they regularize this somehow, but I'm not sure what the precise geometric meaning of that operation is. And because of that, so far it's not very clear how to deal with this. I mean, one can still describe this as a motion on coadjoint orbits of the group for in the case of point vortices. But this is this is very heuristic, I'd say, in the sense that it's not even clear why there should be a group in the case of point vortices, because again, when you start integrating flows with point vortices, then you get this infinite twists at this point. So this is not even a diffeomorphism anymore. This is a more singular map, and it's not very clear what kind of structure these diffeomorphisms have.
Okay, thanks.
Yeah, no, thank you. And yeah, vortex filaments, it's a similar problem, but it's even more complicated than point vortices.
So I don't know if someone else has questions, but I do have a question. So the group of volume preserving diffeomorphisms has various properties. For example, it's a perfect group. Is there some similar statement here about this groupoid, this vertex groupoid?
So we do not know much about the structure of this groupoid so far. So, well, of course, the next step would be to understand the structure of the groupoid to see if one can actually, well, obtain any results about the fluid motion, well, this type of fluid motions using the groupoid. And, well, there are many things that are known about the group of volume preserving diffeomorphisms, and in particular about its geometry with respect to the L2 metric. And many of these results, they have interpretations in terms of fluids. And well, it seems that in the groupoid case, well, it's the geometry is somewhat more complicated than in the group case. So some results that hold in the group case are no longer valid. But in general, we do not understand this really well at this point.
What is an example of a result that it's valid in the group case but not in the groupoid?
So there's no definite results, but For instance, in the group case, well, one of the results in the group case is that if you fix a particular point, then you can okay, so it's not a result about the group, but it's a result about its Riemannian geometry. So you can look at the sectional curvatures of the metric on the group, and if you fix a point, it's a function of direction. Well, you can fix one direction and view it as a function of the other direction. And then there's, for a group, the sectional curvature, well, it's a function on an infinite dimensional sphere, and in principle it can be unbounded, but it turns out that for a group it's still bounded. So here, well, it seems that this is no longer the case, and we suspect that, well, so this, well, as I said, this problem of vortex sheets, it's known to be not very well behaved. In particular, in some cases, the solutions do not depend continuously on the initial conditions. And we suspect that this is related to this kind of unbounded curvature phenomena. But as I said, well, we really no definite statement.
Okay, thank you. Are there any other questions for Anton? Right. Well, if not, let me just remind you that next week the seminar is going to be on the Eastern European calendar, I believe. So it will be 3 hours earlier. And I think we will have Yan-Pen Lee from Toronto giving a talk. So, well, I'll see you all next week then.